All right, let's dive right in. Today, we're going to explore the invisible world of radiation and try to crack a really fundamental puzzle. How do we actually measure how dangerous it is? And more importantly, how do we use that knowledge to keep people safe?
I mean, it seems like a pretty simple question, doesn't it? You've got your Geiger counters that click and beep, but what are those clicks really telling us? Well, figuring that out is one of the great scientific detective stories.
Okay, so if you were trying to solve this, where would you even start? The most obvious first guess, right? Just count the particles hitting something. The more particles, the more danger. Or, okay, maybe it's not the raw count, but the punch they pack, the energy they carry. More energy, more damage. Both sound pretty reasonable, but nope. The reality is way, way trickier. And you know, this quest to find the right way to measure radiation's impact literally forced scientists to rethink some fundamental physics. It's a classic story, really. A bunch of dead ends, a few wait what moments, and then a massive breakthrough. So yeah, let's play detective and follow the clues.
So, first things first, why do we even care so much about measuring this? I mean, radiation is just out there. The thing is, we don't really care about it when it's just zipping through empty space. It's all about what happens when that radiation slams into something.
Yeah, we're talking about the effects. For us, it's about damage to our bodies, which is, the whole point of radiation safety. But it also fries the delicate electronics in satellites, and it makes the very materials in a nuclear reactor brittle and weak over time. So the big mystery at the heart of all this is, what is it about radiation that lets us predict how much damage it's going to do?
And just like in any good mystery novel, the first couple of leads the scientists chased, they went absolutely nowhere. So let's look at these first big ideas and see why they were total dead ends.
Okay, clue number 1, fluence. It's a super simple concept. You just count them. You just count every single particle that zips through a certain area. Seems logical, right? A perfectly good place to start, except it has a huge, deal-breaking flaw. And this is exactly why just counting particles doesn't work. Let's say 1,000 X-ray photons hit you. Okay, now what if 1,000 thermal neutrons hit you instead? The count, the fluence, is exactly the same, 1,000. But the damage to your body? Whoa, it's not even close. Those neutrons can be way, way more dangerous. So fluence, case closed. It's a bust. All right, so if counting is out, what's next? Well, what if we measure the energy they're carrying? Their kinetic energy. This idea is called energy fluence. And this feels like we're getting warmer, right? I mean, it takes energy to do damage. But nope, this lead also went cold. And the reason why is pretty mind-blowing.
This quote right here is the whole ballgame. Remember those thermal neutrons? The crazy thing is they have practically zero kinetic energy. So if we're just measuring the energy they carry in, the energy fluence, they should be harmless. But they're not. They're super damaging. And why? Because when that slow little neutron bumps into, say, a hydrogen atom inside you, it can kick off a whole nuclear reaction that creates a brand new, super fast, high-energy proton. And that's the breakthrough. It's not about the energy coming in, it's about the energy being deposited.
And there it is, the aha moment, the big reveal. The true measure of how dangerous radiation isn't about the energy it's carrying, it's about the energy it leaves behind in the target. It is all about energy deposition.
So how does this actually happen? Well, it's a multi-step process. Step 1, an uncharged particle, like a neutron or a photon, comes in and smacks into an atom. Step 2, that collision creates a new particle, an energetic charged one, like an electron or a proton. Step 3 is the important one. This new charged particle goes tearing through the material, bumping into other atoms and knocking their electrons loose. That's where the damage happens. And finally, step 4, some energy might just fly out the other side. So the key, the absolute key, is to figure out how much energy actually got left behind in the chaos. And this idea gives us the single most important quantity in this whole field, the absorbed dose. The unit is the gray, or GY for short. And its definition is just beautiful in its simplicity. It's just the amount of energy dropped off in 1 kilogram of stuff. That's it. This is the bedrock, the physical foundation for everything else.
Now, there's a sister concept to this called KERMA. It's a bit of an acronym, stands for kinetic energy released in matter. Think of it like this. KERMA is the money the first particle gives to the second particle at the start of its journey. Absorbed dose is how much of that money the second particle actually spends inside the material. They're not always the same, but in some very specific, ideal situations, they can be.
And this is a picture of that ideal situation. It's called charged particle equilibrium. So just imagine that little box is a tiny chunk of your body. All it means is that for every energetic charged particle that flies out of that box, another one with the exact same energy flies in. The energy books are perfectly balanced, and when you have that perfect balance, Kerma and absorbed dose become the same number. And trust me, that makes the math way, way easier for scientists.
So, we're done. Case closed, right? Just measure the absorbed dose and call it a day. If only it were that simple. Nope. Our detective story has one more major plot twist, and its name is biology.
And here it is. This is the big one. A gray is not a gray. Let me say that again. A gray is not always a gray. You can get 1 gray of dose from alpha particles and 1 gray of dose from X-rays. It's the exact same amount of energy deposited, but the damage to your cells? The alpha particle is devastatingly worse. It's because of how the energy is delivered. Think of it like a shotgun blast right up close versus being hit with a bunch of tiny pebbles. Same total energy, totally different outcome. So, to put a number on this, scientists came up with something called relative biological effectiveness, or RBE. It's pretty straightforward. Let's say you need 2 grays of X-rays to kill a certain number of cells in a lab. But for alpha particles, it only takes 0.2 grays to do the same job. You just divide the two, and you find out the RBE for those alpha particles is 10. That means they're 10 times more biologically damaging for the same amount of absorbed dose.
But, and this is a huge but, RBE is a nightmare for writing safety rules. Why? Because it's not a fixed number. It changes depending on the type of radiation, the type of tissue, liver, bone, whatever. What you're measuring, are you looking at cell death or mutations? It even changes based on how fast the dose comes in. You can't base a safety regulation on a number that's always shifting. You need something solid, something standardized.
And so, we get to the solution, the quality factor. We just call it Q. Think of it as a simplified, agreed-upon average value that stands in for that messy RBE. So now the process is simple. You take your physical measurement, the absorbed dose in grays, you multiply it by this quality factor, which is different for different types of radiation. And what you get is a new thing called dose equivalent, and its unit is the sievert. That is the number that matters for safety.
Okay, let's take a breath. We followed a ton of clues here, right? We started with fluence, which was a bust. We found the breakthrough with absorbed dose and its cousin Kerma. Then biology threw a wrench in the works, which gave us the quality factor. So now let's put all the pieces of the puzzle together and see the grand strategy, the master plan for how we get from a random particle flying through the air to a real safety limit for a human being.
And boom, this flowchart, this is the whole shebang right here. You start at the top with just radiation existing out in the world. The first step is to measure its fluence. Yeah, we're back to just counting particles. But then comes the secret sauce, right here in the middle, the response function. This is a chunk of math and physics that magically turns that particle count into a real physical dose, like absorbed dose. And then, for the final step, you multiply by those biological factors we just talked about, and out pops the number that tells you if you're safe or not.
That response function, that's really the heart of everything. It's the mathematical bridge that connects the cause, the radiation out in the environment, to the effect, the dose, inside a person or a thing. It's packed with all the complicated physics of how these particles give up their energy. Honestly, figuring that out was the key that unlocked this entire scientific mystery. So look how far we've come. We started with a really simple but wrong idea, just counting particles. And we've ended up with this incredibly sophisticated system that pulls in physics, energy deposition, and even biology. And this isn't just some textbook exercise, you know? This knowledge, this is what lets us build the detectors that keep nuclear workers safe. It's how we fine-tune radiation therapy to kill cancer while saving healthy tissue. And it's absolutely essential for figuring out how to shield astronauts on a long trip to Mars. The detective story is far from over, but now, finally, we have the right tools to solve the next set of clues.